Hello. Yeah, it's all fine. Here. Hey, this is Coffee Compiler Club. And anything to do with compilers and language runtimes and SSA and garbage collection and typing systems and null and not the null are all fair game. I reserve the right to moderate, never had to do it. I typically don't have an agenda. Today I do. And then after that agenda is done, it should take me like 10 or 15 minutes. We'll just go back to free form discussion. You're all being recorded. You'll be up on YouTube within a couple hours. If you don't like that, bail out now. Otherwise, here we go. So I threw out a link to slides. Did anyone fail to get the slides link? And then I will throw it up on the shared here. Do you know when I want to say anything first? We have a couple of new people. Let's just do that first. We have a couple of new people. Going left to right on my screen, it'll be Steve Manuel goes first. So like 10 seconds, 15 seconds. What do you do? Why are you here?
Sure. Hey, hello, everybody. Nice to meet you. I may be the newest compiler engineer in the group. I just started my first official role as a compiler engineer for a quantum hardware company called Rigetti. And I work on our LLVM integration targeting our quantum hardware and working on implementing a intermediate representation called quantum intermediate representation. So I've done some AST tooling and CodeGen and stuff like that in the past, but this is my first proper compiler job. So I'm here to learn and soak it all in.
Excellent. All right. Ganesh, is that how you pronounce it?
Yeah. So I don't really do any compiler stuff other than the class I took in college, but I was always interested in runtime stuff, and I've been watching these videos and watched a lot of Cliff's talk, so I had some questions I wanted to ask. Yeah.
Well, let me go through my agenda, and at some point we'll hit free form and just open your mouth and say something, because if you wait for me to raise your hand or you raise your hand, it'll never happen. You got to actually say something. Everyone else here has been here before, so I'll just let it go at that. Welcome to new folks, whatever. I do have a handful of large shirts left, which I'm reserving for people who actually show up and participate anyway. I had some YouTube requests for shirts, like, no, you gotta actually participate. And that being said, let me go ahead and flip into.
You should have some requirements beyond just participation. Like they should actually prove that they can do what's your favorite algorithm again with the top and bottom?
I don't care. Any DAG walk will do, but whatever. So strongly connected components is like a more complicated DAG, but whatever.
To be honest, I'm glad I already have mine, because I'm pretty sure I would fail.
Let me see, move my app over here where I can see. Okay, so here we go. So this is like Cliff rambling on what the hell to do with SSA. So you should stop me and ask questions if anything's confusing, because otherwise you just it doesn't hang together. So my goal here is to build SSA, and I want to do it. I have this technique that's just super easy. At least in my opinion, it's super easy, and it has like 4 or 5 basic operations you do over and over again as you walk through the program text, and that's it. And you get SSA out the end. And what do I mean by SSA? Well, I mean a single name for every program value or program point of interest. And what do I mean by name? Well, in my case, I'm going to use a node, a graph node, but a node is just a C-style pointer to a data structure. Could be a tuple. You could call it a tuple if you like. And you can rename that pointer with %p and a printf to some ASCII string that represents a pointer. And you can rename it to x sub 0 or distance or y or x sub 15, whatever you want, as long as the name is unique. So all these forms are functionally equivalent. The graph node, the pointer of the graph node, the text form of the pointer, some name like x15, all equivalent within alpha renaming, which is the whole point of SSA in the first place. So the goal here is to make an SSA form not to be minimal. I will present it as a graph, but if you just do an alpha renaming, you got it as text, you got it as tuples, you got it as x sub 0, like you see in all academic papers, same thing. And I'm going to parse it straight from program text, but it's equivalent to parsing from an AST modulo. You got the tree already, and here I'm going to assume I'm going to fake the tree as you go on. So I'm going to start by doing some simple examples, and we'll step up to a little bit more complicated. So x squared plus y squared, that's my input text. My output's going to be graph SSA, which I have this mystery blob on the right for nodes and edges, equivalent to some text form, like I said, with a pretty print over the resulting DAG. So I have a text cursor. I'm going to walk it through the program text. I'm going to ignore all kinds of parsing issues, like how do I tell what an identifier is or a number, or how do I tell what an operator is or what's its precedence. I'm skipping all the details. This isn't about parsing. This is about building SSA form. I assume you guys can parse. If you can't, go online, learn. Little different parsing if you have an AST, but equivalently the same. You're walking an AST instead of walking program text. I'm going to have an expression stack, which I'm going to start to empty. That's the stack on the bottom center. And I have a map from names to nodes. It's kind of a flexible, what you mean by map here. If you're doing program text, I'll probably have a hash map from strings to nodes. If I'm doing Java bytecodes, the name is just the register number out of the Java local variable register number set. And in fact, I use equivalently an array list, a vector in C++ to do the same mapping. So it's just a map from what you call a name in your program to a node in the IR. Okay, so in this expression, X and Y have been predefined. So they exist already. So I'm going to show them in blue. I have a map pointing to them, saying that if you find the name X, this is the node it refers to. I put a little X next to the node, but not in the body of the node, because the node is some operation like an add or read from standard in or some basic operation. I don't know what it is, but it is not the name X. It is an operation that produces the value for X. That's what I'm showing when I show this IR. So now we're going to walk it through. So you're going to parse something, you get an identifier, it's an X, I look it up, I find a node mapping, I push it on my expression stack. So that's the only thing that happened there. I parse a multiply, it's some sort of operator, insert your favorite precedence parsing strategy here. I'm like ignoring that issue. So somewhere it got saved, perhaps via recursive descent, perhaps via an explicit stack, I don't care. Parse another X, push it, it's all very boring. Oh, I ended by operator multiply, so what do? Well, I pop the two nodes for the binary operator, I build an IR node, could be a tuple, token, however you build your IR. And I put the edges that I just popped in for the input edges, and then I put that result back on my stack. And if you think I'm building an expression DAG, you are exactly correct, because they are exactly synonymously, ambiguously equivalent to SSA without control flow. So I'm going to repeat. There's a plus, push it on stack, save for later, partial Y, push in stack, operator multiply, save it for later, push a Y or find a Y, push on your stack. Pop the two values for the multiply, you get another multiply node in the IR. Now I'm going to pop the two things, and one more guy, pop two things for the add, push them on the stack, and I'm done with this expression. So I'm going to finish up the assignment and say, well, I have a dist here. I'll put a mapping in it in the map, pop the node off the expression stack and push it. And that's it for no control flow, straight up walkthrough stuff here. Let me pick up Zen here.
What is dist?
A fake name for distance squared. I didn't put the square root in because I didn't want to deal with.
It's the symbol you're defining.
Yes, symbol I'm defining. Dist is equal to x squared plus y squared. Yes. Let me find Zen. Here he goes. So, okay, fine. So this is an expression DAG. So there's no control flow. It's exactly the same as SSA form. These are synonymous terms if you don't have control flow. So I also built UStef edges directly, which are very helpful for all kinds of program analysis and optimization. But you can flip them and get DU edges by walking the graph in reverse. And in fact, I build them at the same time, both directions, but I'm only going to show UStef edges because the UStef edges carry the semantic meaning. The def use edges just show you who's using the value you just produced. So are we all clear on any questions, what I got right here?
Well, okay, this is going to be a nasty question. So if you have, so I noticed that when you have two arrows pointing to X. So
Yep.
when you flip it, that means you have two arrows coming from X.
Yes.
Like, I don't know.
This is perfect. Perfect question. Okay. UStef edges have semantic meaning based on their ordering. A subtraction of A minus B is different from B minus A. You cannot reverse those edges. DU edges do not have semantic meaning based on their ordering. They're just a list. However, if you do a graph traversal and you're trying to match a DU edge and a UD edge, you do have an issue if you start from the DU side that you see the same node twice in your list and you need to map it to two different edges accordingly. When I do serious optimization using this style, and I do this all the time, that particular scenario arises, but only very rarely. And usually it suffices to walk the other way and the problem goes away. But sometimes I have to pay attention. But it's very rare. But your key observation is the edges, the USTEF edges are semantically meaningful in their order. DU edges are not. If you walk the DU edges, they don't have an obvious mapping to the UD edges. If you were to store them in a list format, which I do, if you have explicit edge data structures, you already have the DU, the edges are both directional already. I don't use explicit edge structures because it's so much faster. Hey, Theodore's going to make it. Let me make sure. Actually, my participant list shrank, so I don't see who's waiting in line. Anyone else here before I carry on?
Hey.
Hey, you made it. That was. I get my once a week check-in that you're okay. That's all. I care. Fine.
Yeah.
All right.
The time here is 1 hour earlier again.
Oh, for time zone things.
Yeah.
Ah.
I forgot.
Yeah, that's okay. No, I forget too. My wife would beat me on the head and then I remember, but otherwise I forget. All right, let's roll on here. So done with this. People who missed, sorry, we can come back and retouch it. So let's look at some control flow. So I have some control flow now, and this talk is not about control flow. So I'm just going to use a generic basic blocks. Now, when I do this myself, of course, I use CF nodes, which has a CFG embedded within it directly. It's presented in a different way, which isn't part of this talk. It's not helpful here. So generic basic blocks, right? So I put a black whale blue, or I put a box around my stuff saying, this is a basic block. And I'm going to do this maxing operation where I take X and say, oh, the ball is going to bounce off the wall. So I'm going to cap it at the wall or whatever. Okay, so I have I've removed Y and dist for clutter. I've added wall in, and I just made some space. I have my basic blocks sort of permanently there. Moving on, I'm going to just start parsing X greater than wall. So I parse X, I push it on my expression stack, I parse wall, I pop and build the operation. I have a greater than test for X and wall, and just like subtract and divide, the order is meaningful on the direction there. And now what do I do? Well, I've hit the end of a basic block that has a conditional. This would be the same test you do. So I had an if, but I had a little tighter expression writing for my screen real estate to do it question mark colon, but it's the same thing for an if test. So you pop the node and you put it somewhere connected to the basic block as your test block. Different people do this different ways. Often the last tuple in a basic block is the expression test. If it's an in-way test, you have a requirement that the last tuple in the block point be the test value, but different, like I said, different people do it different ways. In the sea of nodes, it's just another edge, like all the other edges in the sea of nodes, to an if node, which represents the condition at the basic block end. Let's not go there. Okay, so I also need 2 new basic blocks for 2 of my false arms. So I'm just going to throw them up as empty shells. I'm going to fill them in as I parse. I need map clones. Well, I need a map per basic block. I'm done with the first basic block, but now I have 2 basic blocks where I had 1. I need 2 maps. They're identical. I'm going to clone the map. I'm going to save one and reuse it for the true side, and the new one will be on the false side, but they're different maps. So I'm going to do the true side first. I'm going to walk through the same parsing thing. I'll look up wall, find my map, push on my expression, and I'm done with the true side because it's trivial. Fine. And so that ends the true block. And the block is empty because in this case, it's going to be empty anyhow. Fine, it's empty. But I need to keep the map. And in fact, I'm going to have a unique map for every in-process piece of parsing text that's running in parallel. So every time you have a nested if then else, every pending else that hasn't been parsed yet ends up with a expression stack, a map and a stack waiting, hanging out, holding the mapping for name to IR at that program point, and I'll come back to them when I restart the parse on that side of things. So the true side got done. It didn't do any side effects, so no, the mapping didn't change. If I go to the false side now, do the same lookup. Again, the mapping doesn't change. Again, the block's empty, but I have an expression stack and maps all filled out for the two different blocks. Now I have two different maps. I need to merge because I'm hitting the merge point in the control flow graph. So at every merge point in the control flow graph, I'm going to get maps from the different arms that are being merged. I'm going to align them and merge them. I merge both my maps and my expression stacks. If you're merging at statement boundaries, your expression stack's always empty. But if you're merging like a trinary here, your expression stack has something and the maps do whatever they say. And what's it mean to merge maps? Well, it makes one map from two, that's the merge. And it's just same goes to same and different goes to phi. And what do I mean by that? I mean, I look up the equivalent X and X in the two different maps. If they point to the same thing, I'm just going to use that node in the merged map. And if I look up two different things, and same thing in two different maps, and they point to something different, I get a phi out of it. And what's a phi? Well, I'm going to ignore that for now. In fact, it's really, really not important until much later. Stupidly, it seems like it ought to be the crucial thing. It's not. It's the least crucial thing. I'm going to treat it like it's a random binary operator, like a divide or subtract. It takes two inputs. It produces a result. It behaves in all other ways like a tuple or a node in the graph IR. Equivalently, you treat it just the same when you walk it in the basic block. You inject them in the basic block. You walk them in the basic block. You do whatever the hell to do with them. The only thing that's different is when you ask for the semantic meaning when you're doing semantic optimizations, like an add of 3 and 4 is 7. That's a semantic optimization. You constant fold it. An add of something in 0 is just the something. That's a semantic optimization. Phi has similar semantic optimization concept. The rules are a little different for it than other nodes, but an add's not the same as a multiply. Every node's got different semantic meaning for what you do to optimize. Same for phis. But that's the only place they're different. Everywhere else, they're just another node. Okay, enough ranting on that. So clean out map, just make it easier to read. What do I look at? My expression stacks? They point to different things. One points to X, one points to wall. Yeah, they're different. Put a phi in. There's my phi. You'll notice my edges are blue now out of the phi. That's because they're part of the IR, not part of the building of the IR. And they point in order. The order is swapped because that's how the expression was parsed. Or that's how the expression has meaning. But that's it. And then I have one map expression pointing to the, expression stack pointing to the one node. That's the merged expression stack. I'll merge the maps. They're trivial because they're all the same. So I just get the one map. This is the end result of that. The merge is done. The stack points to the phi. X points to X. Wall points to wall. Everything else points to whatever they pointed to before. I trim them out. And now I'm done with this statement. I can do the assignment, which I did same as I did dist assignment. I pop the node off the expression stack and I assign it in the map. And this assignment changes X from where it had been to a new value for X, a new node for X. And this is where SSA gets its renaming properties that you see in these papers, or X sub 0 and X sub 1. One of these would be X0 and one of them X1. For me, it's the node for the top left blue circle for it used to be X, and the new one is the phi. That's the new name, it's the phi, or the address of the token for the node or the tuple in the graph. That's the name for that X now. So are you all clear with that? So this is question time, because now I'm going to do loops. Okay, I'm rolling on. I didn't think this would take very long. It's not. So here's a loop. It does a stupid thing because you have to fit it on a slide. So it just sums the first numbers from 1 to 10. And the talk's not about building a CFG, so I'm going to start with the CFG in place. I could build a CFG incrementally as I parse. Obviously, every parser does. That's not important here. I'm not going to do that. So here's the CFG I've started with. And I'm just going to start parsing the program text. Yeah, I'm going to go a little faster. So X equals sum equals 0. I'm just going to parse it out as there's a map on the upper right pointing to X and sum pointing to the 0 node. So 0 is the IR token for obviously a 0. And I hit a new blockhead, which happens to be a loop. So at this point, I need to clone my map. So I just make a clone. It's a shallow copy of the map. It's literally like, you know, whatever shallow copy clone versions. I don't know. It's everyone's trivial shallow copy. And then I'm going to do a thing where I'm going to insert the fees right now because I don't know what's going to change around the back edge. So for every name in the map, I insert a fee. And the fee will point to, on its left edge, to what the map used to point to. And the right edge, I don't know yet because I haven't got that parsed yet. So I'm going to leave the right edge blank or null or not yet filled in or whatever you want to say is pending. It's not yet done. And I named my two maps on the right, one head and one loop. One's the loop head, one's the loop body. I don't actually name them when I do this in real life. Every basic block that's part of a pending parse structure has a map. And when I'm done parsing it, I fold the map into whatever and throw the extra one away. Here I have two because I have a control flow merge point. I need to come with a back edge, which I haven't found yet. And I got to keep my head around. So I'm going to roll forward from here. Now the loop body points at the fees. So I'm going to look up x less than 10. I point to the fee and not to the 0. And I do x less than 10 like I did before with, you know, other x less than wall. Produce the same kind of thing, tie it off to the basic block as an exit point. Now I've hit an exit block that branches. I need to clone the map for both sides, or keep one for the one and make a clone for the printf side, which I'm not going to show right here, but you can imagine there's a mapping from x and sum available for the printf. So when the printf asks for what is sum, I can find the value of sum at the loop exit point, which is not the bottom of this loop. So I get down to the body of the loop, and I start with sum plus equals x, and the add points to the old value of sum and the current value of x and produces a new value for sum with an assignment, which I'm just going to do quick through. And you see sum points to the plus now. And you get x plus 1, same story. The value for x moves forward, but the plus points to the old value of x and some new, you know, constant 1 that plus plus produces. And I have two maps now, a loop map and a head map. And I'm going to merge them in the next slide. So take a look at them now because the next slide went too quick to the merge, but the merge is stupidly obvious. I just took the back edges from the loop and plugged in the empty slots of the fees, and I got my fucking arrows backwards. Damn it. I have my uStuff edges backwards on the back edge of the fee. Pretend these are reversed. I can probably reverse them painfully on the spot. And it's not worth it. Yes, it's not worth it. Okay. So I'll do that later offline. And that's the, that's the end of the loop. And I'll go one more slide here. I picked up the SSA edge for the printf on sum, but that's the SSA form for a loop. And the only operations I have are enable our expression stack, do lookups in the stack, or the expression, and do pushes and pops in the stack, name lookups on the map, assign or reassign into the map, clone the map. There's a merge operation where I look to that's the end of it. That's all the code that's necessary, plus whatever you have to do to parse. It's fast, it's easy. So let me go one more, take questions here, and I have one more set of slides to sort of clean up the situation. And then this prezo is done. We're all like absorbing here. So let me roll on, people can think about it. So when I made that loop header, I get a lot of junk fees that I didn't show. So I'm going to show them now. So imagine y or dist or wall as variables that were in my map. At the head of the loop, I said, for every variable, whether I don't care what you are, I'm going to make a fee for you. So I get a fee for y here. And my loop and my head maps point to the y fee, which as I roll forward and I hit the merge point, it just makes a self-cycle fee. It's a junk fee. It means nothing. It not means that it's an identity function. It's like add of 0. It's semantically morally equivalent to multiply by 1 or add of 0. What do I do about it? Well, it pollutes the graph. It makes the IR thicker and heavier, and it makes it difficult to do certain optimizations. So I want to get rid of it. I'm going to use a peephole rule. What's a peephole rule? I draw a circle around some region of graph, and I look at my input and my output edges. I'm going to preserve the semantic meaning of the input and the output edges, but I'm going to rewrite the inside of the graph. inside of that circled area. And the rewrite looks like, just get rid of it. Point the input edge to the output edge, and you're done. And you'll notice that my edge color changed because I removed an edge that was in the IR and made it just part of the parsing state again. But that's because my edges are all just plain old pointers, and I can't tell one color from another anyhow. And I don't need to. It's not part of, there's semantic meaning to that edge color. So that's the cleanup for an empty junk fee. It happens as soon as you fold in at the loop head. All the obviously didn't touch it variables in the loop body just have their fees disappear at that time. They were only there just in case.
So how do you select the part of the graph you look at? You're just going through it at a regular interval or whatever?
Okay, so you're very soft in your voice.
Oh, sorry. I said, so how are you selecting the part of the graph you're actually looking at, like the peephole?
Oh, for the peepholes, like the parser uses whatever you use for parsing technology. The peepholes, at the time that I do this set of peepholes, I do it at the moment that I'm doing the merge at a loopback edge. So the parser has told me I am remerging something that I split off from earlier as a loop. And I know at that point that this may have been a loop or might be, I did the conservative thing, I threw in all these extra fees. Now I'm getting rid of them at that time. Okay, there's another piece to this though, and that's this piece. The text on the left has changed. So I can write those, apply those rewrite rules anytime I want, at any part of the graph, at every place. And you can do serious optimization this way, and C2 totally does it. So one of the things that happens out of this is that dead code elimination dies in the parser. Because when you remove the last edge to a node because it got rewritten or the map went out of scope, that node has no uses. And because I'm building DU edges, I have a count of them. When the count of the use goes to 0, I delete the node, which recursively makes other nodes go deleted. So they all die in the parser. And they actually die at cost no more than the bulk size of them to produce the allocation. And I recycle them back onto an arena where they just get reused again immediately. They even stay hot in your L1 cache. The empty nodes just get recycled in your L1 cache. So dead code elimination comes out of the parser at really not much more cost than the cost to parse the text in the first place. It's like really fast here. But other things happen.
That suggests the dead code never even got typed.
That's correct. The dead code never got typed.
Yeah, well, that's a problem if you were hoping that it was type checked.
So, all right, yeah, no, it's fair. So in the land of Java bytecodes, the verifier ran first, and I already got type checked. In the land of AA, I made a command decision that dead code does not have an interesting type, and I'm gonna throw it away, untyped. You're allowed to have type errors on dead code on purpose. So that would be, say, I have an if-def Darwin, else if Linux, else if Windows, and each of the different arms, I have some code that does an OS specific thing and has the wrong argument count and the wrong type for this and the wrong blah, blah, blah. And on the wrong operating system platform, it's just wrong. I don't care for those type errors. So I don't need a macro preprocessor to get rid of them without typing. I get rid of them without typing by dropping them on the floor. If you have a command decision that says, in my language, dead code still must type, then you can't throw it away yet. You're correct. And you have to decide, what it means to throw it away. This is building DU edges and UD DU edges. And if the decision is, I still want to keep them, even as they have no uses, then you might leave them in your basic block until you're done with the typing pass, as a for instance. But don't toss upon 0. And both in AA and Java bytecodes, I toss upon hitting 0 uses. There are a bunch of people trying to say something at the same time and stop. So now would be a good time to say something or ask.
Quick question. In a more complex loop scenario, maybe there's branching or a nested loop, are you setting up the same kind of placeholder fees that you were in the outer loop or in each parent branch?
Yeah, every potential back edge entry point gets the placeholder fees.
Okay.
So you get a set of them every time you nest a loop. And then they unwind in reverse order as the parser runs across them. If you have like go-tos, like Java does, C compilers have done this in the past for, yeah, you get every time you might have a back edge, you throw in the conservative set of fees. And when the parser is done and says, no more people will jump to this here go-to label, I will now declare it done. And if I had any extra edges placeholder waiting, they're all gone. And now it's time to run the peepholes to get rid of them. And because the peepholes change the graph structure, they might invert from loop inside out, get rid of a nested stack of fees of an unused variable, right? It was live in, it was live out, it's unused. In the body of nested loops, you get nested fees for every time in, they peel inside out. So as you run peepholes, you usually get new opportunities for more peepholes. So it is useful to run the peepholes in a loop until no more apply before you start parsing again. And that's something I do in AA. And in C2, I parsed I peepholed one time on every node as it was made in the first place. And I peepholed one time on loop back edges. And then I saved all the other peepholes till I got them to parsing. And then I ran the peepholes to a closure with a work list, just an iterative work list. Repeat until work list goes dry, pull a node off the work list, apply a peephole. If one applied, put all its neighbors on the work list. If one did not apply, nothing happens, you just throw it away and carry on. When the work list runs dry, you're done with peepholes. That set of optimizations gets you halfway to GCC-02 in time that is linear in the size of the program text, but in time is actually like stupendously fast. If you look at where time goes in C2's optimizer, 20–30% is the parser because of horrific things the Java bytecode semantics have. 40% is the register allocator. 10% or less is in the peepholes, and they do 90% of your optimizations outside of loops. And the other like 10–20% is doing loop hacks. That's where the time goes. The peepholes are the cheapest thing to do, and they provide the most bang for the buck by far.
Cool. Thank you.
So these maps of names don't care where the names came from.
That's
some of them
correct.
will be defined locally, some of them will be arguments, some of them are from the context where the function was defined.
Yep.
They just don't care.
They just don't care. That's right. If your semantic meaning is this is the value for this token, this name X, then that's what it is. And that's what the map carries. Yep.
So is
And
there any
identically, just what you said, sorry, Alan, what you said, if when I start a function on entry, I produce an initial map that points to the arguments. And I have some IR token that says, I'm an argument. However, I start my initial function basic block entry point. And different people do it different ways. C of nodes does it differently from basic block, standard basic block stuff. But I totally done the standard basic block thing. And you just had some stupid arg tuple. It was named a arg tuple. And it was just in the first basic block of the function, and it carried the name for that argument, and everyone knew what it meant. Yeah, same thing. Sorry, Alan, go.
Yeah, so I was just wondering, whether there was a way to assign this map to a variable. So like you could say, oh yes, this is the state of my variable names at this time, and this is the state of the variable names at that time. And
so for debug info in Java, totally what happens is that mapping is made, and we use an IR node for the mapping. The IR node is called a safe point node because it represents a Java safe point, and it carries the semantic behavior of that program point. And I don't put them in everywhere because I'm not doing debugging everywhere that way. For optimizer purposes, safe points only have to happen every now and then. And when you break at a Java bytecode, what really happens is you stop the JITted code at the nearest safe point, and then you single step forward to your breakpoint. And then as soon as you're broken out of the, at any safe point, you remap it back to Java bytecodes, right? And then now you're in the interpreter and you single step along and fine. But the whole point of it, where's the debug info? It's you basically took this mapping here and declared it an IR node that carries the semantic meaning for who points to what. And literally that's what C2 does. That mapping is in a node called safe point node, and that is the mapping. It's not a hash table, it's not a this, no, it's a safe point node. And if I need to stop and put one in the graph, I do so. Generally on a de-optimization path where you're going to bail out to the interpreter anyhow, because you hit a range check that never failed before. So you have to have all the semantic meaning. So you have a safe point at that time. It's the one you were parsing with. You tie it off to jump to the interpreter here and die. And it's now a node in the IR. So I don't have a separate mapping node type. I just use an IR node. But this is sea of nodes, like refinements. The actual thing you would do, yeah, do whatever you want to do with that mapping, and totally you can bake it into your IR as debug info. And Hotspot does exactly that.
So SSA is a graph representation of your program.
No,
And
SSA is a mathematical representation, like all programs, where the special property is every name in the program is unique.
Mhm.
You can't use X twice, but you can use X sub 0, X sub 1, or node names or pointers or whatever. So in my screen I'm showing right here, a academic paper version would rename X, the initial X for what's assigned to 0, to be X sub 0. The while X less than 10 value to be assigned X1, X sub 1. The X plus plus, the bottom plus at the very bottom of the screen, that would be X2. The phi would merge X0 and X2 to make a new X1.
so the names are globally unique,
The
or
names are globally unique.
So Theodore, I mean, basically it takes a spaghetti code, if you will.
Mhm,
So code with mutable variables and whatnot. And it breaks it up into tiny little blocks, each of which does, I'm going to exaggerate, Cliff, but each of which does exactly one assignment.
yeah, single static assignment. Okay, SSA.
Every variable is
That's-
assigned once.
That's the whole thing. That's it.
Mhm. Oh, you mean it's defined so small a step, if you will, so you can track the progress of the program.
Well,
not-
it's easier to reason about when you don't have mutable variables.
Yes.
So what SSA does is it breaks everything down so there's no mutable variables.
Oh,
Yeah,
okay.
that's the main thing.
That's kind of important.
And it's like the blocks can be as large or small as they need to be. It's just you can never, once something's assigned, it can't be changed.
Yeah.
If you want to change it, make a new block.
And new variable, new block. Yeah.
Right. Yes. Well, by making a new block, you make a new,
New variable.
theoretically, you
Yeah.
make a new variable. Right.
Now, within that context, you can present that in a bunch of ways. I did it by saying, if I have an X sub 2 or a bunch of X's names subscripted 0, 1, 2 in, I'm going to rename them to some random ASCII string that looks like a pointer, which I'll then rename to an actual pointer, which I then rename to a node in the graph. It's all alpha renaming. No semantic difference between any of those formats. But as a pointer into the graph, you have a very cheap and easy way to do optimization now. Everything is directly available to you at a pointer chase away.
The optimization by means of rewriting the.
Not all optimizations go by graph rewriting, but a lot of them do. And all the sort of usual trivial things that you think about, your usual constant folding, you do address math, reshuffling, so the address math folds up lighter, all that kind of stuff, that all does in graph people rules.
Oh.
I canonicalize the add so that the constants to the right and the constants all fold up on an array address, which is always, offset plus X times scale plus blah, blah, blah. You reshuffle those, canonicalize those all with people rules.
The image that comes to my mind is that old communication lines with a bunch of slots, and rewrite them as you will to route the communication wherever it needs to go.
Okay, I like my circle around some piece of graph, and I zoom in to people and say, within this region only, I understand exactly what goes on, and I can do something within this region only without being aware of anything else.
But the key,
Theodore's point is actually pretty useful, though, when you think about assigning registers, for example.
I'm not doing register allocation here very much.
Yep. I'm just
Okay.
saying, you can imagine, you can imagine there's some minimum number of plugs you need in Theodore's example, which basically ends up being
Yeah.
Yeah.
Yeah, we can do register allocation another time.
So the key point here that is all represented as one framework to be able to mount the graph rewrite. So it's built from the same stuff. It's just a matter of how you write, how you connect them.
I think that sounds right. I want them connected such that everyone's singly assigned. The graph happens to also have that property. It cannot not have that property.
Yeah.
But I need that property in the first place is what the building is about. Yeah. Having had the property in a graph format, I can now do very simple rewrite rules.
Yeah.
And do them iteratively in linear time. It's very easy to prove that it's hard linear time.
So the graph is somehow the underlying framework you represented.
Yes.
So
yes.
So that circle is, no matter all stuff is represented by nodes. So the program semantics is how you connect all the nodes.
Yeah.
So the rewrite can be done because it's all the same stuff. It's just how it's connected.
Yeah. Yeah.
Oh, okay. I missed the presentation. Damn it! I wanted to see it.
Well, I can go to the start and run through, but you have the slides. You have a link to the slides.
I will rewatch it when it's.
Okay. Yeah.
Damn it.
Hey, I had a question, Cliff, which was if you're building a mutable data structure as you parse.
Yeah.
Is it one thread, or is this somehow? I mean, how do you, if you want to like parallelize your parsing?
I don't parallelize my parsing.
Okay, well, that was my question.
You know, PMake, right, does parallel unrelated C compiles. That's my parallel parsing. If you have a big enough project you would care for parallelism, you probably have independent files that are going to be parsed independently at the file boundary.
Right, file boundary.
Yeah.
So
it's just because the overhead, like technically, I could make a people rewrite rule that worked in parallel over a large graph. Like if the parser is a single threaded walking forward is building graph IR as it goes, you could have multiple unrelated threads doing people optimizations as long as they lock the perimeter of that red circle, they lock all the nodes input and out, they mutate inside and then they unlock. The problem with that is that the overhead of doing that far exceeds just a fast single threaded processor like whipping through it.
Well, I was thinking actually different files. I mean, if you have different files, I have one data structure per file.
No, it's one data structure per basic block. Yes, it's one per file. Every file is its own thing. Yes, that's parallel right there. But in fact, I only need a map per basic block. I only need a map per basic block that is actively being parsed at the moment. So you get a couple of them according to the nested depth of your loop nesting control flow or if branching in your program text. So you end up with 5 or 10 as kind of the peak normal, and the average of like 3 or 2 or something pretty modest.
I wonder if any like database companies that do like jitting use these kind of like optimize as you parse techniques, because they probably care more about compile time, especially for small queries and so on.
Not that I'm aware of, and I have recently, last year, mid-COVID, talked to a database startup company that was doing it the wrong way, and I couldn't convince them. We had a long, fruitful discussion, but in the end, we parted ways.
So you'll never get this kind of like cache reuse that you get with this one if you have like clean layers where the size of your parse output spills the cache, and then you like do another optimization pass, right?
Yeah, right. So when I do this for C2, I worked really hard to go really fast and paid a lot of attention to things. The people rules that I applied on the spot were just on the immediately local graph neighborhood until that local graph neighborhood ran out, and they didn't go far and wide. And the returning graphs, the deleting nodes went back onto an arena by unpopping a stack, basically, an allocation pointer. I unpopped it. And that got back most of the things I had just allocated if there was an immediate cleanup. So in the land of Java bytecodes, you get a lot of repeated computation of like null pointer checks and array range checks. So these happen over and over again as you talk. A is equal to A sub I is equal to B sub I plus C sub I. You get a whole lot of identical checks going on there. they all get found with people rules instantly in the graph. They all get recycled immediately. You build the node, you look it up in the IR, which turns into a V call that says, optimize me, please, with the people rule. And the self-optimizing on the one node says, I'm a fee and I optimize like this. And he does his thing. He says, here's a new version of me that's better than the old one. Or he says, I got nothing. And he puts a null back, says nothing. And as soon as I got a hit, I uncycled him from the graph, cleaned up his edges a little bit, and then went again at whoever he came back with and allowed the rinse repeat until that quit happening. That got rid of like half of Java bytecode semantic IR, 2/3 more like straight out of the parser. It was like a huge win. Now, when that was done and I had a pile of IR and a pile of peoples that could be applied, but it didn't go outside of the local guys. As soon as you had back edges for loops, I didn't close those off at that point. I would then go do basically double buffering. I would read the IR on the left-hand side, produce a copy on the right-hand side, getting rid of dead code as you went by it deleted, it didn't get copied, didn't get touched, it went to 0, so you ignored it and carried on. Only the live shit went to the right after it peopled, and then I took the left arena, which is now empty of things that have been walked through, and declared my new free arena. The right arena was smaller, tighter, had more optimized. I did my next optimization pass on it, copying it in the left arena. And I flipped back and forth between arenas, copying the IR from one to the other as it went through a dramatic transformation. In-place updates for small peoples just stayed in the one side or the other. Things like loop rewrites where I had to restructure things whole cloth would get copied from left to right. But those two arenas would basically sit in your L2, probably not your L1. And you'd never touch main memory while you're like screwing around with the IR until it stabilized.
You just mentioned the loop transformation. I think it should make loop unrolling fairly simple, right?
Yeah. Okay. So let's talk about loop unrolling here as a fun. Let me get a little cleaner. This is fine. Whatever. So loop unrolling in general, there's the cheap version and there's the heavyweight version. Hotspot does them both. The cheap version is where you look at this graph IR and you see in the middle a less than 10. The one input comes from a fee and the other input comes from a constant. So if I push the less than through the fee, make a copy on both arms, look at both the back edge there, I'll have one that says less than 0, 0 less than 10. I have another one that says, well, it follows the back edge around the fee to the plus at the bottom, and it becomes x plus 1 less than 10. Okay, ignoring control flow, I can keep pushing things up through a fee, which effectively incrementally peels the loop. The loop is a cycle, it spins forever. It has an output for my useDef edges, not def use, but useDef goes up and has an exit out. But I can peel the loop by rotating the clock on it, tick, 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 one at a time, like an egg timer rotates its clock. And things that hit the fee go up through it, and they get cloned, one for the back edge and one for the going up. Okay, so that's sort of my intuition of what's going on there. Pragmatically, what usefully happens is that things that happen only on the first iteration of a loop get usefully peeled out, and they happen once before the loop instead of in the body of the loop. The usual one for this is a null check on an array. I said A sub I is equal to B sub I because I'm doing a fucking system array copy. Okay, I have to check for A for null before I can check for length. What's the null check on A? Well, that's a loop invariant. If I peel the loop and do A sub 0 is equal to B sub 0, I null check A and B before the loop. And in the body of the loop, then I can declare the A test for null is now dead. Because if I look backwards from the A test for null in this example, which I don't have a picture of, so it's hard to imagine what I'm talking about. If I look backwards from an if it's in the body of the loop through the loop header fee, I see another task just above it. And because I'm doing a graph thing, it's 1-2 steps away. I have a redundant null check. I can get rid of the one in the body of the loop. And the loop body got simpler by no null checks. So I totally do the sleazy, cheesy, peel the loop one iteration incrementally, normally just to get rid of constants and shit that are easy. In the main loop ops, I force peel one iteration to make sure I got them all, because the people version doesn't guarantee it unless you hard force it to peel the entire body, because there might be things that are a little bit further in that that are outside the range of your people. That said, if I just people parsed a few things that had no gain to peel, I peel this constant x less than 10, it made no gain to my program. It doubled the number of less than 10s I have. One collapsed, so I still have the less than 10. It didn't help me any in terms of program size. But if I peel again, oh, suddenly I get an if test I can get rid of, and there's real progress. So I do the people like I just described, to incrementally peel loops for the easy, cheesy stuff at the head of a loop boundary. Also, all control flow diamonds and all that kind of stuff, that's all easy, cheesy, peel up, same thing. In the loop proper, I will just stop and do a loop thing where I declare this is a loop, clone it, get a copy up front, patch all the edges up so it copies right. I clone a tail because I have exit range checks, and then I adjust the boundaries of the starter and the end loops so that they cover my range checked areas where I'm unsure of the correctness. And then the main body, I can get rid of the range checks, which I explicitly like range check, get rid of. And then that's the loop ops, is a major whole transformation that really does like a big rewrite. So, you know, those are the two main things I do. I do p-poles and I do loops. And I guess the other one, of course, is register allocation as a performance hack. Instruction selection is trivial, doesn't really change performance. Inlining is done at parse time, where I just stop at a call site and say, wait a second, let me change the parser from the next instruction, the basic block, to the head of the thing I'm going to inline and parse from there.
You find you get more value from peeling the first and last iteration of the loop than from unrolling it, so you can try and do 4 times through at a time?
Yeah, the things are done in order, and each time I ask the question, is there profit? So the first thing you do is you peel, which almost always is profit. I hardly ever not peel. And then that gets rid of null checks in the body of the loop. Then I look and see if I have any confusion about the range checks. So if somebody says, if I runs from 0 to n, a sub I and b sub I, well, I don't know the length of a and b or anything related to n, which is the loop trip count. But somebody says I is -2 to plus n plus 3, and I have an array of I -7 and b I plus 5. It's like it's confusing. I do a bunch of normalization on the array math, and I'm still left with this thing that says, you know, if a's length is less than n minus 5, I'm going to blow up or whatever, right? And the loop ends at n, and something happened. So I do a pre-loop and I say, take all the worst case underflow bailouts, take the max of them. That's the pre-loop trip count. Run them with range checks. It's a small count, or I don't care. Hey, if your loop doesn't trip but 3 times, I don't fucking care. You run the pre-loop and you're done. It didn't matter left or right. If your loop runs 1,000,000 iterations, the main loop doesn't need that underflow check, and it will run the 1,000,000 times. And the 3 of 1,000,000 is 1 part in 1,000,000, and I don't care. And the pre-loop just no cost. Same for the post loop for the overflows in that direction. Now my main loop has no range checks and no null checks. Suddenly it gets small, and I have this heuristic that says, if this loop is small and I have reason to believe it trips a lot, double it. And that's your unroll by 2. And then optimize it with the p-poles in the loop iter pass. Just use normal people rolls to it stabilizes. Now look at it again. Is it still small? Double it again. Repeat, double, until it gets big. Or I hit some, hey, I just took your entire loop and declared it as, you know, power of 2 logarithmic, power of 2 execution strategy, all with constants, which people write dumbass micro benchmark loops that do this kind of thing, where the value can be pre-computed by some kind of complicated closed form solution. I end up eating them up in powers of 2, where I do your closed form solution by alternating you took or didn't take an entire power of 2 of the body of the thing. But mostly for the real kind of loops where you do real work, you unroll the main loop is small enough, it unrolls 2, 4, 8 times, something like that, varies, and then you're done. It's good enough. There's also actually a little unrolling diddle where I do for cache line alignment as well, where I go back to the pre-loop and I say, oh, and also add 7 and mod 8 or add 8 mod 7, whatever, and this gets you aligned to a cache line start for the right side usually, and I'll start prefetching on that, and the x86 will just prefetch on the read side. And if you're an ARM chip or a Spark or a Azul or Itanium or whatever, I'll insert the prefetches on the read side, but they don't have to be so precisely aligned. This has to be a cache line apart. So prefetching can happen here as well, manually, or I arrange it to be convenient for the processor to do it for me. But I totally screw around to make prefetching handling. But that's all about loop optimizations. It's nothing to do with GraphIR. This is what you do if you had a standard classic Fortran pile of tuples for loops. If you had to do range checks in Fortran, you would do something like I just described. It had nothing to do with GraphIR.
So for this SSA, is it going to treat functions as special? Or is my tail recursion going to basically end up with the same graph as a while loop would?
Okay, so those are two different questions. So function calls for what I do in this GraphIR is I put a tuple or a node, which has a bunch of input edges, one for every argument you have, because I also represent control flow in the sea of nodes, but you wouldn't if you're doing basic blocks. So that's a difference. I put a control edge in. Because I also do memory updates, semantically meaningful memory updates. Somebody's trying to chat me, gotta run. Hey, nice seeing you, Steve. There's a memory edge for the call. If I do loads and stores, classic loads and stores for field references and field updates in structs or whatever, then you get a memory edge involved, which I'm not showing because it's however you want to present your semantic meaning. A lot of people don't like having a memory edge concept, but then they can't reorder the loads and stores freely. They have to have an aliasing intelligence pass that does reordering there. As soon as I put an edge for them, I can reorder them freely and optimize them freely, which is what Hotspot does for actually, honestly, all the gains you ever need out of alias analysis at essentially no cost. That those papers were written and done, by the way, almost 20 years ago. Hey, what about this version of aliasing versus that version? The answer is you do equivalence class aliasing. It gets you 95% of the performance gain you're going to get out of your best possible, super most expensive Oracle aliasing that's really complicated. But the equivalence class aliasing can be done in the graph here at essentially no cost, like no cost, not even minor cost, no cost. And that's a big difference. So there's a gain there to be had. You should just go it this way. Wow, people are coming and going all over. Oh, there's a time zone change. Got somebody. Oh. Hey, Simon. All right.
Hello.
Hey, we're done answering. We're in the Q&A section of building SSA.
You go by the time zone.
You might have been time zone hit.
Did I arrive an hour late?
Yep.
Oh,
That's
interesting.
exactly on the dot.
Oh man. Oh man. All right. Yeah.
And remember,
Nothing.
There's only two challenges in computers, right? Off by one bugs and time.
Off by 1 week.
Off by one time zone.
Yep. All of the above.
Next week it will be fine again. No worries.
Yeah.
Really? Did the US change?
Yeah, well, California did.
Interesting.
There are like 4 time zones in the US.
1 week earlier.
Okay.
Yeah, 1 week earlier than anyone else. I don't know why.
Oh, I don't know either. California is a big farming state.
The US is going to get rid of the whole daylight savings, hopefully this year.
Right. It was for farmers way back in the 1800s. California is a giant farming state.
It was for the World War, apparently.
Okay, I got it for farming, but maybe.
Are they staying in the winter time or in the summertime then?
I'm in summertime now.
No, if the daylight saving time is abolished, which time is the real one? No, sorry.
It would be permanent daylight savings time.
Each
Noon
country
being, sun being directly up at 1 o'clock.
Summer is the correct time. So we would be getting rid of the winter time.
In Europe, each country will have to choose in which time zone they want to stay.
Yeah, I think they try to
dream of the day when humanity only has 24 time zones.
Oh, everybody who ever does meaning with time. Well, I did that fintech startup, and every exchange on the planet had a different time, and the vendor, the seller and the buyer were in different time zones, and everybody talked about time zones in a different way. Mostly those things predated time zone issues, so they didn't record time zones. So there was always a default time zone that was never mentioned. That varied all over the map for every possible different reason within exchanges as well as across. Just a nightmare to sort out the damn time zone.
Sometime we should have a good argument which one is better, UTC-1, UTC-2, or UTC-3.
I'll hand you guys knives in a small enclosed room, and I'll wait to see what comes out.
And we should argue how they differ from GMT as well. That's a good one.
No, stop.
I will say I was staring at a bug for a while before I realized that GPS epoch and Unix epoch distance between them is not an integer number of seconds.
I mean, the Google guys actually did this discussion, which time zone is better. I mean, have you ever tried to format a date in Go?
Yeah, Java got Jota time, which does a pretty good job. And I think they made it even the official standard at some point.
So Chris, it's not as hard as like playing music in Linux, but it's pretty hard.
All right. Well, I claim that this sounds like a good Swatch International time. Geez. Now
So now we all want to see your SSA parser for timestamps, right?
Yeah. Well, fortunately, SSA and timestamp parsing are unrelated. H2O does time parsing in a big way. And I tried every possible existing thing on the planet, and eventually got all of the official Java ones to throw any count of undocumented exceptions. They threw exceptions they claimed they could not throw from their documentation. Every one of them would throw them every time on certain kinds of data sets from the time zone parser, no matter what you did. So I eventually wrote a fucking manual time parser that is mostly stupid and mostly correct. That's the trick on it. There's like a 99% solution that I took. And then if you have a special time zone issue after that, you are welcome to go tell the parser, this is my special time zone, and he'll take your special time zone through Jota time and parse it that way. But if you're not special and you don't touch any of the time buttons, there's a 99% chance I will read all your times correctly in like 50 lines of code.
Yeah, that kind of reminds me of trying to regex an email address. You get like 99% correct, but you never get a regex which parses everything correctly. It's a nightmare.
Yeah, and it's not worth it. I know that was my observation. Just not worth it.
Yep, I had one last question about this SSA stuff before we maybe switch topics. But how do you model like volatile stores and like the memory model stuff in this? Do you represent them as usedef stuff as well, or?
Yeah. So now we're talking about GraphIR as a more general thing as opposed to building SSA. So it for memory related things, so loads and stores, I have a memory edge, which carries the state of memory, like you might carry the number 5 or a pointer, whatever. That forces ordering upon memory operations. If they're in a different alias class, these are different memory edge. And things that are different alias class would be shit like the same class object, but with different fields within it. So I have a person has a name, has a phone number field. Well, there's no way the name field and the phone number field can ever alias. They're in a different alias class. They give it edges in the graph. They can never have a memory happens before relationship between them, other than the standard sort of volatile thing that can say, hey, I have to do something here with everybody. If they're both volatile and you do something, then all your volatiles get aligned. And exactly I do that by throwing in a memory fence node, which gathers up all the related memory edges and produces one out that everyone then reads from as they
Okay.
Yeah.
Makes sense.
And then that particular edge prevents ordering. The actual machine code representation of that edge varies by platform. Frequently on an x86, it's empty.
Yeah.
You just need a line in the sand, and the line can move related to all operations except memory. So it only has memory edges, and add, subtract, +1, x++, less than 10. Those are all independent, unrelated. And they all float around the graph. And when you come finally do machine code selection, instruction placement, then you decide where that line in the sand goes by declaring, and here's where I put this node in my final basic block layout. And when I emit machine code, it emits nothing, but it's a line in the sand.
So how do you represent volatile?
Just what I said. I put a fence in as needed. There's an IR node in the C2IR called memory fence.
So it's local, it can just move around, and only if it's volatile do you need the fences.
Everybody can move around according to their USDF edges allowance. So all nodes, so they're ever getting the sea of nodes. Within, if you do the basic block only, everyone within a basic block can move around according to the DAG that is within a basic block. The DAG has no ordering other than DAG order. So you don't have to have a tuple order. You have a DAG order, and the DAG order is I walk the DAG in whatever order I wanted. I got an order and a DAG. Fine. So if I go to sea of nodes, the ordering becomes multiple instructions, like extended basic blocks, but even more extended. And within that, they can order any way they like as long as they obey their edge orderings. So same for memory ops. Volatile is another memory op. It has edge orderings. It has edges that represent the ordering relationship that was presented to it by the parser. But then after that, it can order however things want to reorder. And there's obvious, clean, easy algorithms to go produce a reasonable order when it's time to come out of the graph and into machine code that's laid out. There's an obvious way to walk the graph to get an ordering that's legit and actually reasonable. Like it pays attention to block frequencies, execution frequencies, and tries to move things out of loops if it can, because it's loop invariant. So it doesn't have a dependency on the basic block in the loop, and the loop has high execution frequency. So you shuffle things around. Those are the obvious algorithms for how this works, and it's all published stuff. But the freedom to move gets you the freedom to do optimization, both semantically and ordering. In the case of memory ops, it's frequently ordering matters because you want to get some stall time before your memory barriers have to like cause you to wait. So that answers the question.
Yeah, I mean, I do want stall time and to reorder the memory, but I also want to have the ability to say, grab the lock, then mutate the thing, then release the lock, and know that I'm not going to grab the lock, release the lock, then mutate the thing.
No, as soon as you grab the lock, memory ordering went down. When you said mutate the thing, you loaded it. Where did he get his memory edge from? He got it from the lock's memory fence. And you said,
okay, got it.
Okay, then you did a store, which took its memory edge from the lock on entry as well, but it produced a memory edge, which is what was used by the unlock at the end. And so those loads and stores got bound inside the lock region by the memory edges.
Yeah, got it.
Mostly,
You have nested locks, and you recognize you have nested locks. You can peel off the inner locks, and the memory edges are free to float, and the loads and stores can move inside the larger, greater lock, and so on and so forth. Sorry, Ganesh?
Yeah, this is unrelated, but I wanted to ask about interior pointers and garbage collection. So my main understanding is that it's troubling because when you do the mark, you need to know the start of the object. But are there any other issues with respect to like modifiable interior pointers and like current garbage collection? And then
that's like
then sort of also related is, why doesn't Valhala allow me to modify the struct? Why is it immutable?
Well, okay. So it's immutable because they don't want to track interior pointers.
Mm-hmm.
So they just make a clone of it. And because it's immutable, you can't tell the clones apart.
Yeah.
So then they don't have to deal with moving it. Okay, why is it hard to find the interior pointer? Because the interior pointer looks like the interior thing. It happens to be embedded inside a larger thing.
Mm-hmm.
What is the larger thing that's embedded, and how do you find it?
Yeah, Go does like size classes or like spans or whatever. I wonder what your intuition is about supporting that and allowing you to control layout a little bit better versus losing the efficiency on garbage collection. I don't know how you get that info without like profiling or whatever, but.
So as far as I know, the only obvious answer that exists is you carry some extra weight around on either the pointer or everything that either every pointer or everything every pointer points to, that you use to reverse to go find where you came from. And if you are a standalone object, you didn't come from anything, that's one thing. And if you came from something else, you have to go to the something else and begin moving it.
I think what Go does is they know that within a given virtual address range, it maps to a size class. So you can just do a computation to just find the span header.
Yeah,
and then,
right.
Yeah.
That's an interesting technology. I was thinking about that. You were saying it. And it was.
And then you don't have something per object or like per pointer or whatever.
No, you've done the per object thing by
Yeah,
dividing
yeah,
up into your
yeah,
address space bits.
Yeah.
And the penalty is that as soon as you have large motion between different sized objects, your breakdown of space becomes fragmented endlessly. If you have all the same size of things, and you put a dude in, and you've just done a line size of things of size X, and your dude doesn't land on an X boundary, he must be an interior pointer to an X boundary, and you just round him up to an X boundary and you're good to go. As soon as you have lots of things of different sizes, like you make a lot of these and you delete a lot of them, and then you make a lot of some other size, the things that you just deleted all disappeared, left holes all over your address space. You have to compact them down and then restructure your address space. So you have a new address space where the next space has this other size I have lots of. And if I keep shuffling sizes back and forth and left and right, you rapidly end up where you have very inefficient heap usage.
Especially if you don't have a moving collector like Go
And if
does.
you don't have a moving collector, you're just like shot in the foot. Like I can write a simple program that would run into out of memory error to have 10 objects ever and you get an out of memory error because I just keep recycling the objects and you just spew them out until you're out. And in fact, Gil Tene is really good at this and he likes doing these things. And he has a lot of these test cases where he has programs that will just, crush most allocators and do some stupid thing where he allocates a bunch of things and he throws them away and he allocates a bunch of things, throws them away. The total memory footprint at any given time is a few megabytes of program text. I mean, a few megabytes of functions or objects or whatever. And most allocators go into panic mode and die within minutes. It's amazing. And you can make an allocator that doesn't, plays all the right games, but now it gets hard. I mean, this is without having interior pointers. Interior pointers open a whole other can of worms where things could die on you that way, where you could shoot yourself in the foot. So I'm, like my goal for interior pointers is to say I'm an inlining object, get rid of the object header. It's space savings for having, I have a pixel object has RGB pointers. They're only a byte. There's 3 bytes in the pixel object. But the RGB carries all this semantic meaning. And so I want to have all these functions. I want full on objects for the red, the blue, and the green pixel colors. And I want them to take 1 byte each in the pointer and the pixel object, right? So I want to pack the object in, minimize the space. But in that kind of a scenario, I'm going to know statically what the hell the thing is, the red. And when I want to say, I want to give me a red dot color image rotation thing or whatever I'm doing with chroma coloring, blah, blah, blah. I'm going to inflate it to a red thing and then call a red object on it maybe. And I'm willing to claim or willing to go in a situation where I give up some of the things you would do with a red object to have a red byte in my pixel, because I want to have a billion pixels because that's my color map. That's my color on my screen, right? That's my video game I'm writing. So I just give up it's a whole full class object, which is what the Java value objects proposal is all about. I have some class of objects which are value objects only. They live inside other objects. They lose their object header identity. They lose their personal identity. I can't put them as a solo thing in a hash table, for instance. But they otherwise behave like an object in a lot of contexts. So you give up some of your objectness in exchange for the huge space savings when you have a billion tiny things. And then you don't need an interior pointer. And I'm thinking that's still a reasonable trade-off.
One or like a few more related things is that when you have a moving collector, you are able to better use like huge pages. I wonder what the Azul hardware had, because x86 has like 4K, 2 meg, and 1 gig. Did you also have huge pages for the Azul hardware? And then how did you deal with that?
Yeah, we had. I think we had dual page sizes. We had 1 meg and 4K, and x86 has 2 meg and 4K. The Azul collector on x86 does the 2 meg large pages,
But not the 1 gig. People are still getting slow
and
on
I
using
don't know. Like I left Azul a long time ago, so I don't know if they've added 1 gig support or not. The incremental benefit from 1 gig is probably kind of modest. And maybe it's real, but not necessarily huge.
On the newer chips, they added more 1 gig TLB entries. So Ice Lake onwards, maybe it's more beneficial.
It would probably make sense for large arrays of primitives in Java. Outside of that, it's hard to imagine.
No, even like the general heap space, if you have the moving collector, you get fewer TLB misses, right? If you map the whole
No,
thing.
so in the Azul collector, you use the TLB pages to represent a read barrier, which is how you change let you do the incremental collection. It's a fast, low latency incremental collector, right? How does that work? It has a read barrier. How does a read barrier work? Well, read barrier says when I pull a pointer up from memory, before I let the Java virtual machine see it, I have to pass a test on it. That's a whole fucking lot of tests. How cheap can I make that test? And the way you do it is you double map TLB entries, and it has a pointer bit that's just checked by the act of loading the pointer and doing a TLB reference to it. Okay, the next piece of that one is I take whole pages and I move and compress them one page at a time, but I don't want to necessarily have those pages too big because that goes to latency on when I can declare I have a pointer of an object moved. So I'm with Cameron on this one. Certain classes of very large objects with no interior pointers, I would claim that makes sense for. Other things, it goes to your latency and your garbage collector. And so I'm not excited about it necessarily.
Yeah, in Java's lots of pointers. I mean, that's the other thing. Small objects, lots of pointers.
That's the usual case.
It's a spaghetti model, right?
Yeah.
Other than the arrays of primitives. Yeah.
Yeah.
So this is a trade-off induced by the garbage collector design choice. So if you use like parallel GC that doesn't do these read barrier games, then you'd want to go with the 1 gig
Of
size.
course, is that the Azul collector will give you modest microsecond max pause on 40, 50 gigs a second. 10 years ago on an x86, sure, double that now. So incredible allocation rates, tiny max pause times. And that's an interesting trade-off that a lot of people are excited to make.
Yeah, but certainly for user-facing stuff.
No, high frequency traders, low latency people doing web services, all kinds of folks like that trade-off because it just makes it a no-brainer on the garbage collection side. How many companies have how many engineers whose full-time job it is to fucking tweak GC flags? It's a huge count. That's Azul's market. They sell right to those folks. This guy would love to be doing other things with his life than fucking flipping GC flags. And that's how they sell to.
And there's now,
We always did the
I think,
same
3
thing at
different.
Hastecast.
One at
What's
a
that?
time.
Cameron, go ahead.
Oh, I was going to say there are now 3 GCs, including Azul's, that do that. I think ZGC is one of them, Azul's GC, and there's one more.
Shenandoah.
Yeah.
Probably.
Yeah.
There's actually a recent paper I read. Maybe let me put that in the links section. That's about garbage collector overheads, because when people measure like garbage collector overhead and so on, they don't usually do it in a fixed CPU setting. So you can artificially make your trade-offs like not be real by allocating CPU that the concurrent garbage collector could use. That it might have competed with the application if you were in a fixed cost setting. I mean,
yeah, you can't really judge the performance of the garbage collector unless you have it also lined up with response times.
Oh yeah, yes. Not just like not just max individual pause time.
Right. Yeah, and it has to run for at least a week.
Yes.
So the H2O compute model for doing big data, big math was we ran all cores maxed out doing math, and cores spent doing GC was a negative. Also, we're a batch operated kind of solution. Even at 1 or 2 seconds for a batch, we're still mentally batch model. So we did exactly the parallel collector. As soon as you go to any of the user-facing latency sensitive applications of any kind, they almost always well underspec the processor to keep their latencies down. And they have huge amount of spare CPU cycles that they would happily burn on a faster garbage collector. So this is a well understood problem. And yes, you can tweak it one way or another right away. And H2O totally went down that path and said, look, we don't want the low latency incremental collector. We want fast batch throughput on big arrays of big data.
Yeah, one last question related to GC is that so currently the Go garbage collector, if it hasn't run in 2 minutes, it runs. So, and that's to if you like hold on to a piece of memory and you like release it and say it's like a 10 gigabyte integer,
Right,
You
right.
you want that to go away, obviously.
Right.
So, is there any way without running GC every 2 minutes to get rid of that? Probably not, right? I mean, you have to know that it's dead, and how do you
Right.
know that?
I did it at H2O by having explicit knowledge of the lifetime of only my big data segments. But my big data segments, I track lifetime on. I ref counted them. When the ref count went to 0.
Okay, that's interesting.
Yeah, but this was me handwriting ref counts on only the big data pieces.
Mhm.
All of the control logic, which was 99% of your engineering, that was all standard Java heap shit.
Basically the same thing that we did at Hazelcast for all of the off-heap implementation. You allocate the memory, you know what you need. You can't hear me. Oh God, why is my mic so low today? I said it's basically the same thing that we did at Hazelcast. For all of the off-heap stuff. You allocate the memory, you know the life cycle of your object, or in this case, your cached object. You ref count it and you deallocate whenever you're ready. It's basically the same thing.
Hey, Simon, I'm going to interrupt here. Simon, you had a question in the chat. Did you want to talk about it before you leave?
I think it wasn't a question. I just posted a link to an interesting talk where whether there's a bug in a concurrency library shown, and it turns out that it's related to memory barriers and the differences between ARM and x86. So this was I posted this a few minutes ago when the topic was still on that. So I can recommend the talk. It's really nice explained.
Did you put it? Oh,
I also put it in the Google Docs now.
In Google Docs now. Okay, yeah, cool. Yeah. I had to live that because I had to implement both of those. It was a very exciting time. Everyone claimed this or that, the other thing, and then we discovered that everyone was lying. x86 and ARM both. It's all good. But it'd be fun to read those or watch those. All right, see you.
Hey, I have a follow-up. I think you mentioned you grabbed your nodes out of an arena.
Yeah.
And that's so it's in the cache.
Yeah.
And I just, it seems like like the Valhala is talking about, well, we be nice to have a better fit for modern architectures that has caches now. And so I'm curious how that actually helps. And then just in general, like, is there kind of an impedance mismatch between GC and this architecture of the caching? Like you're just missing reference counting things locally, or you have something, it's almost like you need a little malloc and free or reference counting or something, little immediate free things.
So I wrote the hotspot core JIT as a part of a big C++ program. There ain't no GC. So GC don't matter. You're writing the GC. All right, so the later versions of whatever, Truffle, Valhalla, I don't remember what the names all are, they lived with a GC, which is a reasonable assumption now. Okay, and now you have a performance question of what's the performance cost of using a GC under various kinds of use cases. And for use cases where you have a well understood lifetime you're tracking for other reasons, object pooling can win over a standard collector. So what a standard collector does, bump pointer allocation. Bump pointer allocation gets you a new cache line every time you bump, or however much you go through. And that new cache line has never been in your CPU's instruction D caches since the last GC cycle. 100% guaranteed cache miss. Okay, so prefetching helps some, but you are burning bandwidth. And you are bringing in a line, which means you have to throw out a line. And you throw out a line, of course, the hardware picks a line to throw out that he doesn't like anymore. But it likely had some future use to it because it was a reasonable line and was in the cache in the first place. Except for all the things that you just declared dead because you got done using them because you're cycling through things very fast. So you're making things fast and they have a short lifetime, or you weren't making things fast. If you're making things fast and they all have permanent lifetime, you blow up your heat and run out of memory and you die anyhow. So the typical story is you're making things fast and they're dying fast. Now they're flowing through the processor. They come from memory, they get zeroed in the processor, they get written out after their little use cycle because something else has to come in and they have to get kicked out. So you end up burning bandwidth like there's no tomorrow. You end up continuously flushing your D caches, and you end up with no cache locality on the things that you're always allocating. So if instead you happen to have a reason to track lifetime and you can say, this thing's dead now, I'm going to return it back. And then I'll pull it again. So who does this? Malloc and Free do this all the time directly in C. So that's a giant win for Malloc and Free in terms of performance. In Java, you can object pull, but you can't change the type of an object. Malloc lets you change the type of an object. Java, you can't change the type, but you can throw it on a pool and pull it off, and I do that. There's arenas are a way to do Malloc and Free where you have a little more convenient management of lifetime. And this is what I'm doing in C2, where I bump pointer my arena. And then when I decide a node is dead from peepholes, I unbump it. And it's a stack-like thing. And if I have 2 or 3 things back that got unbumped, I track a few of them. And if I unbump them all eventually, then I take a big jump back and reclaim all that storage. But I don't go very far, and it's all constant count because I want to do this fast. So I end up with things behind in the arena that are dead, and they're going to get garbage collected when I garbage collect the arena. But that's the arena model for C2.
The C++ custom allocator stuff, the custom new allocators.
It's a custom or C++.
I have a lifetime here, so I'm going to create an allocator just for that lifetime. And when it's done, I just the allocator, I delete or recycle it, and everything's gone.
Basically, I know what is uninitialized available memory and what I don't at the language level, and I can specifically say, go back to the uninitialized pile, and then a pull again from the uninitialized pile. This ends up with memory that sits in your L1 or L2 cache, and you recycle in and out of your caches hugely faster.
What is oh, go ahead, Cameron.
I was going to say Malloc and Free are fairly, I mean, we always considered them to be fairly expensive. I mean, they were not quite up there with an IO, but they were pretty close, you know, when we were doing C and assembly and stuff. Like, you know, you avoid Malloc and Free like the plague, or new and delete in C++.
Right. But these
so,
days,
you know, programmers who say, you know, Malloc and Free are fast and garbage collection is slow. First of all, garbage collection can actually be faster, but either way, you know, you're paying a lot for having someone else manage your memory for you.
Yeah,
I consider Malloc and Free having someone else manage your memory for you, even though you have to call them yourself.
well, yeah, the hard part for that one, of course, is the bugs that come out of misuse. And GC fixes, you know, 90% of those bugs.
Yeah, I mean,
not all of them, but a bunch.
I don't ever have bugs, so that's not a problem.
Okay, fair enough.
I had one related question, and it's sort of like a Fredbooks style question, but what improvements or what things do you think made the biggest difference to programming productivity other than garbage collection and pre-written libraries?
Oh, the JIT thing. I like that one. You know, whatever, like people play with functional programming, object-oriented programming. These are all useful things.
You
I don't know if they
step back, Ganesh, and you said garbage collection like it's about collecting garbage. That's not what garbage collection is. If you think garbage collection is about collecting garbage, you've missed 99% of the value of garbage collection.
It's primarily like a productivity thing.
Wait. You cannot have composable libraries if you do not have garbage collection. In C++, if you're building a C++ app, you can use library A and library B, but you just can't use A and B together. You use A, you use B. If A uses B, you're fucked. Right? Done. Gone. Right? Well, before
Lang disagrees.
I mean,
before Rust. Before Rust, this was the case.
Well, I'm saying Boost smart pointers really helped. But
okay.
Before what garbage collection allowed you to do was almost JavaScript randomly, pick 50 or 500 different libraries, use them, allocate stuff, hand stuff back and forth, and nobody had to keep track of anything, which is why we pay full-time engineers to tune GC. That's my point.
Yeah, that's right.
Yep. I agree with that. I was just wondering, other than those two, and
that's pretty big.
Yeah. Because I don't think like object-oriented or functional, I don't think it matters too much.
Well, that's
not even
because you
2x.
haven't written in spaghetti C code since you were a teenager.
Yeah, maybe.
Go back and go write only in spaghetti C code.
Mm-hmm.
And after 2 or 3 years of that, you'll be like, oh my fucking God, where the hell?
Or maybe a slightly more refined question. Can you, like, if you're building like a nuclear power plant, like monitoring thing, can you do 2x better than Java ever? I don't think so. Right?
For a man-critical situation, there are other things that you do independent of the language.
Maybe I shouldn't have chosen nuclear, but just like a
Well,
generic.
that's
yeah.
but that's the deal,
Yeah.
right? So you
Well,
go
what
to
do you
IBM
mean,
Federal
what do you mean by
Systems.
better? Ganesh, what do you mean by better? Define
So
uh,
like time to completion with high quality.
fail. You do better, meaning nobody fucking died, right? That's what man critical means.
I should not have used the nuclear
Okay.
power plant.
Okay, if we're gonna walk away from that one,
Yeah.
then you have a thing that's
Let-
like
Let's pick planes.
not to mention Boeing Max going nose up and butt down or
Oh, God.
anything,
Oh,
you know, as a software fucking bug.
Maybe
That's
something
not-
like
that's an
maybe something
organizational
more
bug. That's a
mundane.
management bug.
Yes.
Those planes crashed because of bad management structure.
Okay, fine. Yes.
Or maybe something more mundane, like if you were to write Microsoft Word or Microsoft Excel.
Right. And now you have an excitement to time to market, time to new features, and time to this and that. The GC thing helped a lot. Java safety helped a lot. You know, C guys like to rant on this, but honestly, I wrote tons in both, and Java just gives you the prettiest crash ever, which is much quicker to debug.
Ganesh, years ago at a company called Borland, I think it was Borland.
Borland did a lot of good.
They wanted to build a spreadsheet to compete with Office. I think it's Borland. Bill, I don't know, you might remember the story. But so they took a team, I think it was 3 or 4 people, and they were using, I want to say it was something like Pink or something, one of these object-oriented systems, and they built the entire thing start to running in less than a week. Like they literally, it was this, they went into a separate room and it was code throwing over the wall to another team to sort it and get it compiling and whatnot. And they built the whole thing in a week. So, you know, their productivity can be pretty impressive, but it usually comes down to the team, right? Like,
yeah.
This is the thing, you know, like having been on the speaker circuit for years, like I know a lot of the authors, and you know, they were brilliant programmers. You know, one of them on a weekend wrote Smalltalk from scratch, and the other guy created the first computer, and this guy built the x86 from leftover toothpicks, right? Amazing guys. And they're like, well, this latest invention of mine, we'll call it stand-up CRUD, I don't know, whatever. And they wrote a book about it, Extreme Stand-Up CRUD or something, right? And they're like, this will solve all your problems. And I'm, you know, the problem is they're just such good programmers. They could have picked the waterfall methodology and COBOL and built anything, Word or Office or Excel or like, you know, so the question isn't what works for like the uber best top 1%. The question is what programming methodologies, tools, whatever, work for the rest of humanity, you know?
Yep.
So do you think programmers are more or less productive than they were in, say, the year 2000 or 1990?
Yeah.
I have 2 answers and they conflict. So if you go back to 1990, you could take an average programmer, and I don't mean that in a complimentary fashion, and they could build from scratch a working GUI system with a database, you know, in a couple of weeks. Nowadays, if you try to do the same thing with, say, Node.js, you know, they'll have a dependency graph of 6,000 packages, and it'll take them 6 months.
Yeah.
So in some ways, our productivity has dropped. I think our complexity has gone up dramatically, which has impacted productivity.
Yes.
In terms of programming, I think the languages and libraries have done wonders. So I have a contradictory answer.
I'm with you on that
I
one.
think you get a point there. It's not that programmers are inherently worse than they were in the past or less efficient, but the complexity went up like quite a bit.
Not necessarily usefully so. Some things got more complex because there's a minimum bound and, you know, it has to be there. A whole lot of shit got more complex that you just don't need it. And one of the things that I always do when I start new projects is I stare hard at what you really need, and I chop out things that add complexity without solving problems. And it usually means when I walk into somebody else's project, I chop 90% of it out. And a month later, we have something that's hugely faster and hugely understandable and easier for every engineer in the company to work with. And I have done this many, many times. There's just so much shit floating around that you just don't need. that everyone's like, oh, we have to have, and then we have to have Node.js, we have dependency chains, we have to have this, and that, and yeah, just like Cameron said, pretty soon you got 6,000 dependencies.
Well, we got Bill, Dave, and Keith on the call who've seen, an awful lot of this, that time period. I mean, what do you guys think?
I was surprised Bill didn't jump in when Ganesh questioned the validity of functional programming.
Well,
I
so
also,
yeah, go ahead. Dave.
go ahead, Bill. Go ahead.
No, go ahead,
I was
Dave.
going to make a joke. You probably had something more
No, no, no.
substantial. My joke is that you should have like a sound generator attached to your feet so we can have music that goes in time with your boom, chicka, boom, chicka, wow, wow.
Yeah, well, boy, so the answer, let's see. There was something beautiful and simple about C programming somehow. I mean, C, the book, I read it on a bus going on spring break in college, and I read the whole thing. And now it's like, there's a lot more. I don't know.
Yeah.
So.
Yeah.
But,
Yeah, if you read the awk book, when you're done, you know awk. JavaScript doesn't work that way.
None, it's not a function.
But I was wondering, I mean, the question I was going to ask about Arena is like, the bump up and down, it's a little bit like a little stack.
It is.
Things that don't go on the stack. Why aren't they on the stack if they can do this?
Because not all of them will get reclaimed, because I have it's an endlessly progressing forward pile of IRM accumulated.
Yeah, it's going like this.
Yes, yes. I get 3 or 4 reuses at the top of the stack before something's permanent and life goes on.
And eventually that's going to have to move to some other place.
Yeah, right. And then when I'm done, do back and forth, back and forth. Okay, I got this. This is my wad of my IR. Okay, I take this and I copy to the next arena down here, where hopefully it shrank and got a little tighter. And then I took it and I said, oh, loop things. And I got bigger and moved up this IR. And then I said, oh, clean up all the junk that out of the unroll all the loops. And we got this one and this IR. Okay, fine. And back and forth you go a few iterations.
Plus,
I said this, plus I added
optimizations that are more difficult too when your data structures are theoretically mutable, visible and mutable from multiple threads. So.
Yeah, I mean, I just do the Java memory model, which meant that I gave up on whatever that I had to honor the memory model.
So I was thinking about the growing complexity question. If you could, in a half-an-hour lecture, explain how a Commodore 64 read a character from the keyboard and drew a pixel to the screen, you could not, in a 1-hour lecture, explain how a modern Windows computer reads a character from the keyboard and draws a pixel to the screen.
Yes, and I think that's a crying shame, because one of the things that I saw as it happened was that people who grew up using those devices learned the fundamentals inside and out, knew exactly how that
6502 was the 6502 for reading the keyboard buffer was -16368, I believe. And then to clear it was -16384.
I had the similar knowledge of how to do it on a Z80 trash 80 for getting the input port. Yeah, and you got a grid of which keys in the keyboard had their grid up and down. You had to debounce the lines individually, and then at the cross point you could declare key press.
And then each computer, so Commodore 64 had its own, Apple had its own, et cetera, using the 6502 would have a different range of memory or multiple ranges of memory for the
I guess you were lucky, Cameron, to have a modern CPU at that time. I had a Kim 1 with a 6502.
Oh,
1K of RAM.
Oh, terrible.
Right, but if you needed to mix, say, Latin characters with Cyrillic characters, you were in serious trouble. Like
you had
no.
Only
ASCII.
Only ASCII, yeah.
Yes.
And now you could draw what you wanted on your pixels on your screen. Trash 80 had a 200 by 400.
So Trash 80 had sprites. Apple had
no, it didn't have sprites built in. Dude, I wrote sprites. You did not have sprites built in.
So I wrote the. Well, at the time,
talking about color computer, or are you talking about Trash 80?
No, I'm talking. Well, the TRS-80s used. Which chip was it? Was it the Zilog? No.
They used the Z80. That's where the Trash 80 came from.
Right.
No sprites in the graphics hardware for my Trash 80s.
Well, that's
I had
why I
a-
learned sprites. Oh, and maybe it was Cocoa. Yeah, color computer.
I had a color computer, which I believe had sprites. Yes.
Yeah, that's the one. But the Apple had these things called shape tables, which were designed by Wozniak, which were basically every byte you'd put 332. So you'd have 3 bits, which were draw and move. So draw was 1 bit, move was up, down, left, right. So that was 2 bits. So you could stack 2 of those in a byte plus a move. So there were 3 possible moves for the last 2 bits. And then that was the table. So you could build any shape you wanted in a small number of bytes. So I actually built a mouse-based graphics editing program on the Apple for quickly designing fonts. That was my introduction to graphics programming.
Oh, I only wrote games, but I got, good graphical games going, but I wrote games.
Well, I built this for fonts and for games. Yeah. So because in the games, the fastest way so you had double buffering. So you had 2 high resolution. So you would draw on one and then flip to the other. And
Yeah, right.
anyway.
Right. Cocoa, yes. Trash 80, no. Trash 80 was characters only, but one of the sets of character classes had 2 by 3 pixels as a total complete grid. So 2 by 3. And then it was like 24 by 80 or 40 by 80 or something for the screen resolution. And you wrote graphics by doing,
It was 25 by 80, I think.
Okay, yeah, it could have been, yeah. And
Which
I had
is what do you mean,
right
2 by
now-
3?
programmers. Sorry, Dave.
What are the
we're like-
units in the 2 by 3?
I'm sorry?
What are the units you're talking about when you
Oh,
say
it was a
2 by
character.
3?
So you had a 25 by 80 character screen. You could put up character, had ABC, ASCII characters. Some of the extra high order 128 to 255 characters were implemented as a 2-bit by 3-bit screen resolution. So each bit was actually like a 4 by 4 grid of block set, because the fonts had more resolution for the display, but the way you could access it was only through character graphics. And one of the character sets said I could set 1 of 6 pixels each individually by having the 2 to the 6th set of characters set aside for that particular graphic. It's very similar to Commodore.
And
The
if I
Commodore
remember-
64 had the lines and edges and you could box the things. They said a bunch of characters set aside for that.
So if I remember correctly as well, that computer also used 2 bytes per character because it had 1 color byte optional or something like that. You
The
could do
Trash 80 was black and white. Or the ones I
I'm
had were all
talking,
black
I'm
and
talking
white.
Cocoa, color computer.
Oh, the Cocoa. Gosh, that came along later in my life, and I played a bunch with it. Did a lot of I did a lot of games. I don't remember now what the color model was. It might have been 2 bytes per.
Does anybody remember why the games that you typed in from magazines had so many pokes? What were we poking? Was that like machine
So
instructions or something?
Poke is actually a move. It's just a
Memory move.
So,
Well, I
so
understand what it does, but I remember these programs in BASIC that would have
Yeah.
data at the end and a whole bunch of
Right.
numbers.
Right.
And
It's
they were
machine
all in
code.
a loop poke.
Graphics.
It was
the
machine
pokes-
code outputs essentially. So not
Yeah,
even
that was
assembly,
machine code.
just straight machine code.
Yeah, some of them would have been some. You're right.
Or-
Some of them would have been graphics.
graphics. So that's how you would load the sprites or the shape tables as you
Yeah.
poke them in.
Yeah.
I
You
see.
pick
I
them and
remember
you
the
paste it.
advancement in computer magazines when they started using checksums with those data statements. It was particularly fun when you would type thousands of lines of programs before the checksums, and then it would just fail, and you had no idea what went wrong.
Hmm.
Yep.
You knew if you got it
Times were
right,
different anyway.
not what was wrong. Yeah.
So
Can you imagine writing down or copying like 1,000-line program from a magazine these days? That was different times.
It was.
You really had to want it. You really had to want it.
That was-
I understood nowadays copying is from Stack Overflow.
For my Kim 1, that was really the only option. I had a hex keypad. It was the only input device.
I was gonna have 2 comments. One is, to some extent, I wonder if we're just remembering our youth fondly.
Oh, yeah. Totally.
Yeah.
Well, and maybe it wasn't as good as we remember.
I'm quite certain it wasn't.
The other one is, maybe it was so new and it was very exciting. Everything was exciting and new.
Yeah.
And there also wasn't like the JavaScript thing. The reason we have to
Oh,
work because
there you go.
that's what the web browser, and if you want to actually do anything that people use, you kind of need to somehow fit into this existing infrastructure and maybe put something on top.
One slightly related thing to that. I agree about a
man.
lot of the
Commodore 64 on display.
Wow. A computer history museum there.
I agree about a lot of the incidental complexity. I wonder how, like, what fraction of it is due to accessing more like hardware acceleration, where you need kind of an API that you can't just poke at the screen.
Some of it, certainly. Graphics chips became amazing, complicated and amazing.
Yeah.
You know, they're billions of times faster than what we had before. And they have a.
Does anybody write their own line drawing algorithm for fun these days?
I would claim it's a useful exercise first year undergrad, but I wouldn't actually, you know, I go
Well,
from
it
there
wasn't-
to vector graphics,
wasn't-
JavaScript to.
Wasn't so much lines as arcs in the real-time course at university.
Okay.
So my solution would draw a graph on the screen of the track layout for this train, and it labeled a bunch of the interesting places on the track, and then you would type a letter, either uppercase or lowercase, and the program would make the train go there, facing one way uppercase and the other way lowercase. And so drawing the arcs was an interesting part of that. There's no floating point stuff back in the early 80s to work with. So,
and no math coprocessor.
Oh, you did
So
fix
for the
math,
people on this call,
right.
if you had to draw a pixel to the screen, what would you reach for? HTML, Qt?
No. You would just set the byte that has that pixel in it. So basically, every byte had a certain number of pixels in it.
No, I'm saying right now, if you needed to build a GUI today, what would you reach for?
I would reach for
HTML.
JavaScript or HTML. Yeah, I would use a web browser.
Yeah, that's why I built the hash function in the browser so you can see it. By the way, I found what the problem was. The random function, it was Chrome, believe it or not.
Oh yeah.
I can share the screen to show you the Chrome is completely was random.
Try it now.
Okay, yeah. Stop one. Okay, fine. Let's open one.
Nice desktop.
Oh yeah.
What's that icon set?
Oh, it was candy something. Candy
Right.
icon. So let me see, let me copy the address because I don't remember it from my old.
Well, we can, do other things while you get it sorted out, and it'll be.
No, I just have to copy the address. I'm ready in just a second. So here is in JavaScript. Yeah, for some reason it's much faster than Chrome. I don't know why. And if you draw the random points, the random int, yeah, evaluate, and it becomes completely random. It covers all the screen, but so
Yeah, I claim I still saw a thread-like beating pattern, which I claim if you ran a test for randomness on would probably pick it up. And claim.
So yeah, but the problem here is in Firefox. I will open another window to see this in Chrome.
Your random int, is that a calculation
so
you wrote, or is that one built into the browser?
No, the random.
So Chrome has just a terrible random number generation or something.
Yeah, that was Chrome for some reason. I don't know.
Yeah, it's probably faster.
Yeah, and in
benchmarking games.
If you see that in Chrome, we will see that pattern of the which emerges side. So here, if evaluated, and that was it. Knows it
clear
wasn't
long black lines.
Yeah, that was the problem.
Oh, it's totally not random.
There's a diamond.
It even looks to be symmetrical. Like if you cut it in the middle, it looks to be like a mirror.
I had already imagined I can already imagine a website generating labyrinth that
Hmm.
then has a remark this only works for Chrome.
It always generates the same pattern. If I create it and redraw it, it generates the same pattern always.
Well, and your
So-
RNG is deterministic.
What did you seed it with?
Random generator. What is the random generator you're using? Do you use this like
This function.
crypto random?
This
Yeah,
function.
Math.random.
I claim your function sucks, but that's okay.
Yeah.
But okay, if I just wanted a random function, I don't want it cryptographic secure.
Yeah,
But
no, not cryptographic.
This is the same function. This is the same function, and it looks still completely random to me. It's more.
Yeah, I
random.
mean,
And it
his
will
get
cover.
random int, his get random int method is perfect. It's just he calls math.random.
Yeah, and here.
So you know, having done a big data science thing, you know, random numbers count for a lot. And if you have a pseudo random function that produces crappy random numbers, you get crappy data science results out.
Yeah. So the problem it's I'm almost certain that the problem is the distribution of the random numbers, but certainly the Firefox generates more random numbers than Chrome.
Yeah.
I don't know why.
It means someone needs to go fix their random number generator. It's
Yeah.
fine. There are thousand tests for random number generator quality. It's amazingly hugely deep field that's entirely exciting to a actually fairly broad set of people.
And back to the errors question, I wrote it in JavaScript because anyone can try it. Otherwise, in Scala native, you have to compile it. You have to do a ton of other things. So we just here you write your head function and see its distribution.
Yeah.
And I will modify it to detect more hash collisions. I have idea of what right now. We spoke the last week. It will make it white or black. Right now, I can make it to gradually move from white to black. That way, it can detect more collisions. It will generate a different pattern.
All right.
Okay.
I want to see if there's an easy way to wrap up here because I have something to do a little this afternoon.
Well.
Any other questions about anything here?
Yeah,
maybe
just a small thing. I really appreciate that Java can do inlining through virtuals because Go can't, and then that is annoying in my current job because there's one thing that's almost always the case, and if you had inlined it, you could remove an allocation and so on. But yeah,
so you choose the wrong language.
Yeah. Too late for that now. Too late for that.
Well, Go wasn't allowed to do inlining of virtual calls because Go is emulating a certain age in software before virtual calls existed. So
yeah,
didn't exist back then.
Kind of feels.
To do it.
It kind of feels that way.
Yes.
Java inlines virtuals. Everyone can. It's not that hard. Sorry.
I'll say with the random number test, I'm convinced that it's relatively easy to prove random numbers are bad and not even computable to prove they're good.
There's a long and deep theory here. Don't go there until you go check out the theory before you make statements like that, because I'm fairly certain that there's some people who have strong opinions about that statement and hard mathematical proofs about it.
All right, I'm off to the literature.
One thing, maybe a topic for the next time. Did you see that upper address ignore is now or is being worked on to be supported for Linux? AMD posted some patches where you can basically tell it to not require canonical pointers for bit 63 to bit 57, so you can stuff arbitrary things in there.
So
Intel also had the linear address masking or something.
Yeah, it's comparable. Yeah. We will be interesting, I guess, to see what's
how will I address my 16 exabytes of memory.
I wonder what's the real world impact of not having to
you can stuff extra stuff in there.
Oh, yeah, people hide things in the bits.
Yeah.
Here they come.
I wonder what's the real world impact there of not having to mask or shift the the custom bits out there every time you
That's what the Zool collector double
reference.
maps TLBs specifically to do that. They double map so that the same two different pointers that differ by 1 bit will land at the same place while they're doing their read barriers. If you're in the mid of a space flip, you get this behavior, and that's part of the goodness of the collector. That's how the collector gets its goodness.
It depends on the density of your pointer reads to like stuff in these extra things that bloats the instruction cache by some fractional percent or whatever.
I'm sorry, there's nothing to do with the iCache.
No, no. So if you have to mask it not in hardware but in software.
Oh, in software masking.
Yeah, then your density of
Yeah, well, in any large random junk Java or C program, actually, loads outnumber stores by like 5 to 1, and they're pretty common. So the masking operation you're talking about actually is pretty common. It has a lot of overhead in terms of volume.
I think Chrome did some interesting measurements there like a year or two ago, where they tried different approaches of like different organizations of how they put the bits in there and how to get rid of them, and it seemed to actually make a measurable difference. They had different strategies and they were also different in performance. So it will be interesting to see what's the performance impact now if the hardware can do it for free. But I'll
IR nodes. Sorry, for the in C2, do you like frequency bitpack the type? Like put some in the pointer and then put some in the in the actual like.
An object header?
No. Yeah, or something like that.
You have an object header.
Yeah. No. I was talking when you're building the IR nodes inside the C2 compiler. Yeah. Where do you store the type of the?
Oh, of the node type?
Yeah.
Okay, in C2, the node type is the virtual table for a C++ object. That is your node type. That is your opcode.
Okay. You don't try to like bitpack it yourself, or?
No, it's not important to have the IR nodes be minimalistically small. It's important that they take a blended strategy between small size and ease of use, because they're going to be doing a whole lot of pointer manipulations and they come and go. And if you spend a lot of energy packing them tiny and unpacking them, as opposed to just walking them for the pointer left and right and then doing graph rewrite, which requires you to change pointers left and right and shuffle bits around as you do, more graph rewrite happens than necessary for compaction for keeping in caches typically. Like after I get the big hit coming out of the parser for Java bytecodes in particular, which have a lot of redundant expansion. So Java bytecodes shrink a lot. After that, you're going to fit probably in an L2 anyhow. And more compaction after that's not going to help a whole lot. But ease of use does help a lot. So
yeah.
All right. We're right on 2 hours. I'm going to claim victory for the Alliance and see everybody next week.
Yeah.
Thanks, Cliff.
All right.
Thanks.
Good to be with you guys.
Enjoyed it.
Cool.
Bye.
Next time.
Thank you.